So let's put this into the Euler-Lagrange formula and find our differential equations of motion. So let's first do with theta 1. Right? So the Euler-Lagrange formula for theta 1 would be dl d theta 1, and I use this purple for theta 1 minus, maybe I'll go back to green, d dt of dl d theta 1 dot, and all of that equals 0. So let's put this in here and see what we get. So let's do the first term first. dl d theta 1. So we're looking for all of the terms that depend explicitly on theta 1. So this is theta 1, but it's theta 1 dot, so we'll ignore this term. Same with this term, same with this term. This term has a theta 1 dot in it, so we need to keep track of this. And these two terms also have theta 1 in them. So we'll have these three terms here will all be in this dl d theta 1. So this is L1, so this minus this term here, and then that should all equal 0. So maybe I should draw a line here. So this is we're just plugging it into the Euler-Lagrange formula. Right, and so dl d theta 1 dot, right? I'll write the d dt out, and we'll do that second. d dt, and now all right, now we have to take the time derivative of this, so we'll rewrite it. And then for this term, theta 2 dot is a function of time, and so are theta 1 and theta 2. So it turns out we need to use the product rule. So now if we look closely here, we can see that this term here actually cancels with a term in here, right? We have, oh, now I've written an M1 as a red one, so let me check if that's actually supposed to be like that. So M1 times the sign. So it looks like it's supposed to be M2, so I wrote it in red, which was correct. M2. So this is M2. Right, M2. This is M2. Right, so these do cancel. So M2 L1 L2. M2 L1 L2. Then there's this term with theta 1 dot times theta 2 dot times the sign of the difference. Well, here's a term with theta 1 dot, theta 2 dot, and the sign of the difference. So this actually cancels with this. So I can write, so without writing it out again, we can see that if we separate, if we distribute this binomial, right, we'll have this term with the theta 1 and this term with the theta 2 dot squared. This actually cancels with this whole thing here. Right? They're the same thing. So here it's negative, this is negative, negative, right? So this is a positive here. So this term, if we multiply all this out, this will be a positive term with this. This is a negative term that looks the same. So they cancel. So one big chunk went away. So now let me rewrite this one more time in the simplest form we're going to see it. All right, and these these two terms almost look like they could combine into something. But this is a little bit different, right? This is the second derivative with respect to theta, and this is the first derivative of theta 2 squared. So these both have units of 1 over time squared, and all of these terms have units of energy, right? This term all combined together. Mass times length squared divided by time squared. Mass times 2 lengths, length squared, divided by time squared. So these are all energy, all the same units. So that's at least one thing to check to make sure everything works out. So now we have this second order differential equation, right? It has derivatives, it has two derivatives with respect to time, and it actually has theta 1 and theta 2 in it. And if we did this for another, so if we apply the Euler-Lagrange equation for theta 2, and we went through more or less the same steps, we would get something like this, and then we'd have a pair of second order differential equations that we could solve to find the motion of this thing, this system, with certain initial conditions. So actually we're still quite a ways away from actually figuring out what this thing looks like, but we found the differential equations, and now we can sort of hand it to a mathematician if we want to think of it that way, and they'll be able to do it for us. Or ideally we could do it ourselves, but we certainly won't in this video. It's already long enough. And this is a crazy enough differential equation where you'd probably use a computer for it anyway. And if you go on Wikipedia, and you look at the page on the double pendulum, there's a nice little video or an animation of this thing kind of swinging around, and it looks kind of crazy. So I encourage you to go take a look at that, and then on your own try finding the differential equation that comes from applying the Euler-Lagrange formula to the other generalized coordinate, the theta 2 coordinate.